for you guys is to think about, well, how does all this tie into what a career would be in geology and geomorphology? And as Mark mentioned, you know, I'm now a dam engineer. So I'm building one of the first new dams in California in the last 30 years. It's not very common today. You hear about all the water issues we have on a regular basis, I'm sure. Water storage is an important part of providing water to everyone, right? It's not the solution. It's furthering the issue. But water management at the end of the day is really the big question. How do we use our water? Who pays for it? And how much do we pay? Unfortunately, as people who live in this state, as residents, we're the ones who end up suffering usually because people who use the most water, well, they have a lot to lose if they misregulate. Anyways, the point of all of this is to say that when you build a dam, for example, you have a very large impact on not just the ground that the dam is built on, but anything that's upstream from it. And the geology and geomorphology of that entire area are paramount to the construction, the safety, and the feasibility of that kind of project. So this matters, all right? And in my case, everything that I'll show you today is the basis of what I do on a day-to-day basis. Okay? And there's many other types of careers that rely on this as well. I'll try to throw that in as I go along. And again, don't hesitate to ask questions. So what is geology? It's simply the study of the planet Earth, right? What is the origin of our planet? Okay? What are the materials that it's made of? What are the processes that shape it? Okay? Geomorphology, in many of the same ways, is simply the study of the Earth's surface. Okay? What are the processes that shape the Earth's surface? What is the history and the origin of the changes that you can see in the landforms? How do these things come to be? Okay? And then, specifically, what you see outside, when you see a hill, when you see a cliff, when you see a valley, what is the relationship of that superficial structure to the ground underneath it? The type of rock that's underneath it. Okay? So, I mean, geologic history, so to speak, goes back long before us, right? And I mean, it goes back to when we realized that the Earth was round and not flat. Okay? In 250 BC, Eratosthenes realized that looking at basically the shadow of different buildings in different places in Egypt at the same time of day was cast differently. Okay? And so he was able to calculate, essentially, knowing the distance between these two structures, knowing the difference in the shadow lengths at the same time of day, he was able to realize that actually the Earth has curvature, and hence it was round. And he was actually able to estimate that it was about 24,233 miles in circumference, which is actually pretty close to what it really is. Think of that, that's 250 BC, okay? Long before calculators, okay? All right. So some of the really most important principles that geology and geomorphology are based on, okay, are really, really, really basic, all right? The first of which, the two first of which Nicholas Steno came up with in the 17th century, the law of horizontality, okay? Think of sand at a beach, okay? Or let's just imagine a bucket of sand. If I pour a bucket of sand out on the ground, how is it going to lay out? It's going to spread out on the ground, right? Well, the idea is the law of horizontality is sediments, sand, for example, or soil, when deposited, when left on the ground, they basically deposit parallel to the ground. So sediments accumulate parallel to the surface that they're deposited on. It's the law of horizontality. Does that make sense? Pretty basic, right? It's paramount to the science. If this wasn't something that we accepted and inherently believed in, nothing would be true. All right? The law of superposition. Imagine now you take a second bucket of a different color sand, right, and pour it on top. You take a third bucket of another color sand and you pour it on top. What do you see? You see layers of sand, okay, of different colors, right? The first sand you laid out on the ground, you laid it on the ground a while before the subsequent layers, right? Hence it's older, okay? So all things being equal, if things haven't been disturbed and moved and upturned and folded and lifted and faulted, okay, the bottom layer is always older than the top layer, okay, which is the basis of the principle of superposition. All right, and that, as a geologist or a geomorphologist, says everything. When you go out into the field, your first assumption is anything that's lower, okay, underneath other rocks is older. All right, now it's not always true. Okay, like I mentioned before, it could be overturned, it could be faulted, it could be displaced. Okay, but that's the basic concept that we build the science on. The third, which is probably the most important, is James Hutton came up with in the 18th century. Essentially, it's the law of uniformitarianism. Okay, meaning that the things that we observe in nature today are true for the future and are true for the past. Meaning, water flows downhill. All right. It was true before, it will be true tomorrow, okay, in our environment. Now, the way water flows through a stream bed, okay, and slowly erodes the ground down, for example, and builds a channel and builds a canyon, okay, well, we have to admit, basically, that that's true today. We observe it. That means that it will be happening also tomorrow, and most likely it was happening yesterday, it was probably happening a million years ago. All right? The other thing is, and this is huge, we basically use the law of uniformitarianism to understand what processes, geologic processes, we observe with satellites and telescopes on other planets. And so when NASA says, on Mars there was water at one point, or some form of liquid, all right? Because they see layers of rocks, sedimentary rocks, on the surface of Mars because we sent a satellite up there and it's taking photos and it's sending it back to us. Well, we're entirely basing our understanding of what we're seeing up there on what we know here. Okay? And that's this law. That's it. If that's not true, nothing else is. Okay? All right. In the 20th century, we started understanding Earth as more of a dynamic environment, meaning that the continents are moving. Okay? You've probably heard of continental drift before. All the continents were not in the place where they are today. Okay? In the past. In fact, the Earth, many, many years ago, did not look at all like it does today. We've done a lot of modeling, okay, to try and figure out what the surface of the Earth would have looked at, for example, 510 million years ago, okay? And based on all these models and our understanding of how the continents move, and I'll get to that in a minute, we know that the Earth most likely evolved over time with the continents moving and drifting to the way we know it today. Does that make sense to everyone? So the Earth is dynamic. It's a constantly changing environment, okay? Not just in our little sphere with our feet on the ground, but the entire planet, okay, as a whole. So that kind of came up, that's where basically the idea of plate tectonics came about. This really revolutionized our science in geology and geomorphology because it introduced the concept that this Earth was changing, and it introduced the concept that, wow, this Earth actually is molten on the inside, right? There's a core, there's molten lava, and then on the very thin crust, there's on the very outer surface, there's this very thin crust of hard stuff. And that's what we're on. Okay, that's where we live. Right? Imagine if you were to take a basketball. Okay? You all familiar with fruit roll-up?
Yeah.
Yeah? If you take fruit roll-up and you were to cover that basketball in fruit roll-up, it's about how thick the Earth's crust is. Okay, relatively speaking. Not very thick. Right? The Earth is enormous. Now, what's happening? We see different plates. Our continents are drifting, but it's not just the continents that are floating around. Okay? There's rock everywhere. The surface is covered. And there's cracks in it, essentially. Okay? We call them plate boundaries. And there's three different types. There's convergent plate boundaries, where the plates are pushing up against each other, and most oftentimes one is subducting under the other. It's being pushed back down into the center of the Earth, essentially. Okay? There's divergent plate boundaries, where essentially the plates are moving away from each other, and lava, magma is coming up to the surface, cooling, and forming rock as it moves away. Okay? And then we have transform plate boundaries, which is specifically what we live in here in California, where you have the plates that are sliding past each other. So let's talk about divergent plate boundaries really quick. The seafloor spreading, have you heard of this term before? Yeah? So essentially, because of heat convection inside the Earth, in the molten lava, okay, you get these heat currents. And that's essentially what's dragging plates apart from each other at the Earth's surface. Okay, the crust is being pulled apart. And at that point, basically there's a thinning and lava comes to the surface. Okay? And as I just mentioned, it cools, it attaches onto the rest of the rock and becomes plate material and then moves away. Okay? So it's just continuously creating more tectonic plate as it separates. Alright? So you get the formation of new crust. In transform plate boundaries, essentially, as I mentioned, things are just sliding past each other. Okay? And you're familiar with the San Andreas Fault in California, right? That is essentially the transform boundary between the North American plate and the Pacific plate. Alright? And that's where we get, basically it creates a fault, a big fault, okay? And that's why we get earthquakes. I'll get to that in a little bit. Convergent plate boundaries, there's two types. There's the kind, the Himalayan type, where there's two continents that are colliding in mountain building. Okay, they're creating these giant, giant mountains. Mount Everest, the tallest mountain in the world. Okay, which, by the way, I don't know if you know this, but it's effectively the tallest mountain in the world. But there are volcanoes that are much taller. Actually, if you count their total height from ground, from the sea floor, the top of the volcano. And in Ecuador, the Mount Chimborazo, the peak of that volcano is technically farther. It's the furthest point from the center of the Earth on the planet. Because it's on the equator, and the Earth technically isn't really round. It's more oval. Okay? So, anyways. The Himalayas are a convergent boundary between two plates. One is not really being pushed under the other. Okay? Typically, like in Japan, you remember the very large earthquake that happened most recently in Japan, alright? That's because Japan is on a subducting margin, okay, where the oceanic plate, which is heavier and denser, is being pushed back down into the innards of the Earth. Okay? And actually, that whole island of Japan is an arc. Okay? It's a volcanic arc that's being compressed and creating mountains there. That's why those islands exist. Okay? And the subducting plate, as it goes back down into the center of the Earth, melts and forms lava. It gets recycled, essentially. That makes sense to everybody? So this is all very, the Earth is constantly moving. We're affected by what we see and what we live in, which is really this fast-paced environment, but the Earth itself has this constant motion. Okay? But as I mentioned, we feel that those dynamics at a different scale on a day-to-day basis, just in the formation of rocks, for example. Okay? Constantly in our environment, are you familiar with the three general types of rocks? Sedimentary, metamorphic, and igneous. Okay? Igneous forms in the depths of continents, essentially. It's from slowly cooling lava, very, very slowly cooling. Creates those big granites in the Sierras, for example. Okay? Metamorphic rocks are formed from metamorphose, from the word metamorphose. They're changed. It's any type of rock that's been taken and compressed and heated up and twisted and makes a new type of rock. Okay? The minerals effectively melt and then recrystallize in the rock as a different type of rock. Okay? Sedimentary rocks are essentially just a rock that is a result of erosion from different types, from other rocks, okay? And deposited and then compressed and re-become rock. That make sense? So the point is that there's this dynamic Earth environment is happening in many different scales, okay? But how fast is it moving? Do you have a good feeling for that?
Very slowly.
Very slowly. How slowly do you think? Let's do a little comparison a little bit. Erosion of a continent happens at about 0.03 millimeters per year. Okay? Not much. And we're talking about, all types of erosion. We're talking about, rain, we're talking about rivers, we're talking about our activity at the Earth's surface, okay, everything. Cutting of the Grand Canyon, the big river of the Grand Canyon is just digging down. That's happening at about 0.7 millimeters per year. Okay? Mount Everest is growing essentially at 4 to 5 millimeters per year, and most recently displaced. Right? Did you hear about that in the big earthquake that just happened in Nepal? Yes? No? A very large earthquake in Nepal, and essentially Mount Everest was displaced by, I think, 3 centimeters. Okay? San Andreas Fault here, the Pacific Plate and the North American Plate are moving past each other at about 25 millimeters per year. That's 2 inches. Okay? Every year those two plates are doing this. What does that mean? We're always waiting for a big earthquake, right? But get this. San Andreas Fault is west of San Francisco, right? San Andreas Fault is east of Los Angeles, right?
One day they're going to be next to each other.
Very possibly. Yeah, it's a long way away, right? But at some point, they're moving towards each other, respectively. Okay. Just to give you a different idea, a snail was about 33 feet an hour, okay? That's 1.6 miles per year. Snails move a lot faster than the Earth does, okay? I like that kind of thing there. All right. So the Earth is estimated to be about 4.5 billion years old. Really, really, really old. But imagine if you were to compress the history of the Earth as a whole into 1 year. What would that look like? All right? Well, basically, from January to March, there wouldn't be much going on. It'd just be this big ball of lava in space. Okay? Then in March, about the oldest rocks will start to form as the Earth is cooling down. In May, the first living things start to appear in these seas, right, in the ocean. The first little living organisms. In late November, land plants and animals start to emerge. Right? Mid-December, I mean, the year's almost over. That's when dinosaurs became dominant. Dinosaurs are a long time ago, right? So, I mean, it's kind of ridiculous. We exist in very little last bits of the life of the Earth so far, to the present. December 26th, dinosaurs would have gone extinct, and the Rocky Mountains would have formed. The evening of December 31st, human-like creatures start to appear. And 1 minute and 15 seconds before midnight, the last ice age ended. And from 11:59 and 45 seconds to 11:59 and 50 seconds, for 5 seconds, Rome ruled. Okay? Rome was like one of the biggest empires of human history, right? 5 seconds in the span of the Earth's life. Okay? 3 seconds before midnight, Columbus discovers America. Anyways, I like that. It's kind of an interesting concept because it really puts different things into perspective, right? The question of scaling. So what happens in the west coast of the United States? As I mentioned earlier, it's a transform plate boundary. The plates are moving past each other very quickly, and they're grinding, okay? They're sticking. And the reason we get earthquakes is because they catch up on each other, and every once in a while they let go, okay? So they're just kind of, they're not smoothly cruising along, okay? They're just grinding up against each other. And they're just slipping every once in a while, which releases energy, which is what causes earthquakes, all right? But it wasn't always a transform plate boundary. The reason the Sierras exist, the reason the Rockies exist, because at one point in time, this was actually a subduction zone, okay? And the remnants of the subduction zone still exist, but up north, towards Oregon and Washington, okay? There's a little plate called the Nazca Plate that was being subducted, or still is being subducted there. There's not much of it left, okay? But where we are, its entirety has been subducted already, so we don't see it anymore. And that's why the Pacific Plate and the North American Plate, where we are sliding past each other. And that's the reason why the geology in California, for example, is so diverse, okay? If you've just been outdoors in California, you'll notice the multitude of types of rocks. We have volcanic rocks, we have igneous rocks, okay? Everywhere you go, it seems to be the geology is just so different. It's because we have this long history of subduction and planes moving past each other, so it's really just created this very diverse geologic environment, all right? Quick question, what is the California State Rock? Do you know? Nobody ever knows this question.
I don't even know that.
We do. We have a state rock, and it's called serpentinite. Serpentinite, yeah. In fact, it's kind of a nasty rock.
Wait, doesn't that say or am I reading?
It does say serpentine, and that should say serpentinite. Thank you for catching.
Okay.
Serpentine would be the mineral form as well. Serpentinite, serpentine, it's a metamorphic rock. Okay, and unfortunately, it weathers very poorly. You'll see it around here a lot, actually. And it weathers to talc. It also weathers to asbestos. That's why we don't like to hang on. Okay, especially in construction. If you ever see serpentinite, like here, stay away. All right. State mineral, gold. Right. There's two things in life. There's the one thing, and then there's gold. All right. State gem. No one ever knows this one either.
Quartz.
Should be quartz. Benitoite. Quartz isn't really actually a gem. It's a mineral, but it's not a gem. I guess you could get gem quality quartz, right?
Well, can you explain what makes something gem quality?
That's actually a very good question. It's just its hardness, it's resilience, it's what do you call it? Well, the structure, yes, but essentially, it's a grade of mineral essentially, because all different minerals can have different. Basically, when you have a mineral in its purest form, it would be a gem. Okay. Once you start to have too many contaminants in it, because they always get mixed up, they're less and less gem quality, so to speak. Okay. So something that very nice pure mineral with good clarity, with good hardness, etc., or whatever the hardness of that mineral is, really, they all vary. Yeah. So, back to the scary stuff, earthquakes. Earthquakes obviously result in quite a bit of different types of damage at the ground surface, and we're affected by it in the homes we live in, right? Homes fall over, and that's something that I deal with on a day-to-day basis. I'm really also a geotechnical engineer, and my job is to build things so that they will survive earthquakes, for example. Okay, or any type of movement of the ground at the Earth's surface. Okay, we live in an environment. We build structures, we build bridges, we build dams, right? But we know that this Earth is such a dynamic environment that we need to know, we need to be sure that the stuff that we build is safe for us to live around and live in, right? We need to be sure that the infrastructure we build will survive any type of natural hazard so that we can still use it, right? What happens if a really large earthquake happens here on the San Andreas Fault and the Hetch Hetchy water system gets cut off from San Francisco? No more drinking water for San Francisco. No more tech industry. Yeah. Huge economic results. Yeah. What happens if the Bay Bridge were to collapse? You know how many people cross the Bay Bridge a day? I think it's, I can't remember, it's something like 800,000 cars a day or something like that. It's a joke. It's a huge amount in one direction. There's a lot of people commuting to the city for work. If you lose that bridge, they're not going to have to swim, right? Anyways. You actually get really, in my opinion, cool things too, like surface fault rupture. When the Napa earthquake happened back in September, did you hear about that one? Yeah, it was a small earthquake. What's really cool about it is you don't see this very often. The Earth's surface, the actual ground surface ruptured. There was a big crack in the ground, okay? And it went straight through people's houses. For me, that was just a huge, interesting thing because we don't see that very often, and we get to see specifically how do the structures we live in fare with cracking ground. Can we live in it? Yeah. There's a rule, there's a law in California called the Elkus Ranch, which basically says that if there's an existing if there's an existing fault, you're not allowed to build. I think it's 50 meters on either side of it. Okay, you have to stay away. Okay, there's a big swath that you can't build on and live in, essentially. Okay. That's so that you don't build your house on a fault, and when the fault moves, your house doesn't get ripped apart and nobody dies. Okay? But the interesting thing is, with our building codes today, we're actually able to build structures that will accommodate these places. Right? And that's really cool to me. Yeah?
Doesn't the Hayward Fault like run through the Cal Stadium or something like that?
Exactly. So that was exactly what I was getting to. In Napa, we saw this very interesting case study where people's homes were torn apart, right? And it was a residential neighborhood, there wasn't any real serious infrastructure. Well, what happens when a fault goes through a big stadium, right? And so if you're familiar with the Cal Stadium, you might know that it was recently rebuilt, right? There's a famous crack in the Cal Stadium that has 6 inches of offset because the Hayward Fault is creeping, okay? But they just tore that thing apart. They kept the outer shell for sentimental reasons, historic reasons. And essentially what do? They built that thing back up. It's just a big foam blocks, okay? That when that earthquake happens, if the stadium is full, those foam blocks should accommodate displacement without having the whole stadium fall apart and hundreds of thousands or maybe just thousands of people die. Okay? I think it's an 80,000 person stadium. Yeah?